in the past few classes, we have been solving some problems related to Module 2. Module 2 is about steady state heat conduction. We have seen some examples on plane wall, some examples on cylinders. We'll also see some examples uh, on systems with heat generation. But mostly we have restricted ourselves to one-dimensional steady state heat conduction, either with generation or without generation. We are yet to do some carry out some problems with the heat generation. We'll do most likely we'll do it today or tomorrow. So for today's and tomorrow's class, the agenda is to continue with solving the numerical problems so that you will be familiar with the nature of questions that can be posed. So as I always say, in heat transfer, uh, a couple of questions are commonly asked. What is the temperature? What is the amount of heat transfer? What is the amount of heat flux? These are the common questions. Sometimes you may also be posed in a different way. For example, to restrict the heat transfer to so much, what will be the thickness? What should be the radius? So these are kind of questions that can be posed. So when you are asked to find out what is the amount of heat transfer, that kind of a problem is classified as an analysis problem. So there's already a system existing, it is functioning. You should only find out what is happening. So what is happening means what is the heat transfer, what is the heat flux, what's the temperature at a particular location. Similarly, the reverse question, you are told to say that the system is restricted to have this much heat transfer, or at least this much heat transfer, or at most this much heat transfer. So that kind of a problems, if you are solving, then what will be the question type is, for this much of heat transfer, what should be the material? What should be the conductivity of the material? What should be the thickness of the material? So that is called as a design problem. So two kinds of problems that you will see here, not just in heat transfer, in any course. So analysis problem and a design problem. So we have done both kinds of problems, and we'll continue to do today and tomorrow also. And as I said, tomorrow I will introduce you to this software called interactive heat transfer, using which you can solve some heat transfer problems. Not all problems, but some heat transfer problems. But it has got some inbuilt functions, which I will introduce to you in the next class, in tomorrow's class. So that is the agenda for today and tomorrow. So we'll continue further with the problems that we are dealing with. So these problems I have taken mostly from a textbook of heat transfer called Impropera and David. Heat transfer by Impropera and David. That is available in our library, as well as the title is available in the syllabus that I gave you, so that if you want, you can purchase it. It's a good book. It's always better to purchase a textbook. So here there is this problem. We'll read the problem carefully and then solve it. Consider a plain composite wall that is composed of two materials having thermal conductivities Ka and Kb. The values are given and thicknesses are given. The contact resistance at the interface between the two materials is known to be 0.3 meter square Kelvin per watt. You see this in this particular problem, this is the new thing, the contact resistance. This is the new thing here. So in this problem, we will consider the contact resistance. Until now, we have considered composite slabs, composite cylinders, and so on. But we assume that the contact resistance is 0, which means the contact is perfect. But practically, that is not the case. There will be some resistance. In this particular problem, we are given this value of contact resistance. Now, what is the unit of thermal resistivity? We have seen this earlier. I have also asked this earlier. I want some answers. What is the unit of thermal resistivity? You can see that the unit of this contact resistance is different from the unit of the thermal resistivity. So we'll have to take care of this. Then material A adjoins a fluid at 20 degrees Celsius, for which H is equal to 10 watt per meter square Kelvin, and material B adjoins a fluid at 40 degrees Celsius, for which H is equal to 20 watt per meter square Kelvin. what is the rate of heat transfer through a wall that is 2 meters high by 2 meters wide? So you are asked to find out what will be the rate of heat transfer, and also we should sketch the temperature distribution. So if you want to sketch the temperature distribution, you should know the temperatures, which means indirectly you are asked to find out the temperatures also, the unknown temperatures also. Only then you can sketch the temperature distribution. So this is the problem. This is the problem of a plain composite wall that and consisting of a minimum number of composites, two composites only. So we have this, and before we go further to solve this problem, let me take you back to composites resist thermal contact. I have seen here, this is the slide describing the composite thermal resistance here, contact resistance. There are two components here, and each component is joined, and unfortunately the joint is not perfect, because of which you will have this kind of discontinuous, and this will give you some resistance. So this resistance will be responsible for a certain temperature drop. Remember, whenever there is a thermal resistance, there will be a certain temperature drop. The lesser the resistance, lesser will be the temperature drop. Higher the resistance, higher will be the temperature drop. So accordingly, we should consider this thermal resistance and calculate. So in composite system, the temperature drop across the interface may be considerable. This is due to contact resistance. Surface roughness is responsible for contact resistance. Surface roughness, the projections on the surfaces will not permit perfect contact. Therefore, these surface roughnesses you see here, these are responsible for this contact resistance. These contact spots are interspersed with the gaps filled with air. So it can be air, or it can be any other material which is poor conductor. Heat transfer is due to conduction across the contact area and conduction or radiation across the gaps. So contact resistance is equivalent to parallel resistances due to contact spots and gaps. So you can see here, this is one resistance, this is another resistance, there are several resistances which are all connected parallelly. So all this need to be considered to be parallel. And if you are able to combine all these parallel resistance into one single resistance, then that single resistance will be in series with the material A and material B. So that is how. For rough surfaces, the resistance is mostly due to gaps, and thermal contact resistance per unit area is given like this: meter square Kelvin per watt. Okay. So this value is given for us in the problem that we are set out to solve. We are given 0.3 meter square per Kelvin, meter square Kelvin per watt. So let us first sketch the diagram and then try to evaluate. So basically there are two materials, A and B, and this is a plain composite wall. So let me draw two materials. Material A and material B. Okay, and we are given K for this as 0.09. K is 0.03, the standard units, watt per meter Kelvin. And the thickness is also given. Thickness of slab A is 8 millimeters and slab B is 16 millimeters. So this is 8 millimeters and this is 16 millimeters. And the contact resistance, thermal resistance due to contact, is 0.3 meter square Kelvin per watt. So that is the contact resistance here. Material A adjoins fluid at 200 degrees Celsius, for which H is equal to 10. So, and fluid, so here T infinity 200 degrees Celsius, H is equal to 10. And material B adjoins a fluid at and H is watt per meter square Kelvin. At what is the rate of heat transfer through a wall that is 2 meters high by 2.5 meter wide? So yeah, so each of this side area is 5 square meters. So we are asked to find what is the heat transfer. So this will be the heat transfer. Let us say. So it's left hand side 200 degrees Celsius, right hand side 40 degrees Celsius. This should be the direction of the heat transfer. So we are asked to find what is the value of Q, rate of heat transfer, and also what is the temperature at these points. So only then we will be able to find out the find out the temperature distribution. Okay, so now first let us look at the contact resistance. Let us resolve this part which is new for this problem so that we can reduce the actual problem to a known type of a problem. So we are given the contact resistance as 0.3 meter square Kelvin per watt. So the actual resistance will be this contact resistance. The symbol is will have some double prime. Okay, that is because it is for a certain area. So the thermal contact resistance is this contact resistivity multiplied by the divided by the area. So this is 0.3 divided by 5. Okay. This is 0.06, 0.06 Kelvin per watt. Remember the unit of thermal resistance is Kelvin per watt. What does it mean? It means that to transfer 1 watt of heat, there will be a certain temperature drop of 0.06 Kelvin in this particular problem. So depending on different materials, so we will have different thermal resistances. So a good conductor will have a low thermal resistance, whereas a bad conductor will have a high thermal resistance. So the drop of temperature to conduct 1 unit of heat energy or rate of heat is the resistance. Okay, so this is the thermal conductive, this is the resistivity, this is the resistance of this particular contact. So this particular contact is behaving as if it is a slab, which is having a resistance of 0.06 Kelvin per watt. So now what we can do is we can reduce the entire problem to a known system of problems, with uh, this resistance taken care of, contact resistance taken care of. So this is slab A. Now this will introduce a new slab in between here, which is representative of the contact resistance. And then there is a slab B. This is A, this is B, and this is contact. So I am calling this as this, B is this one, and this contact resistance is shown as the intermediate slab in between slabs A and B. Okay, so now we have convection environment here, we have convection environment here, and we have thicknesses of each of these, conductivities of A, conductivity of B, thickness of A, thickness of B, and also we know the resistance offered by this particular slab, this particular contact resistance slab. So what we'll do is we'll represent each one of this with a temperature. So this left hand side convective environment is, let us say, T infinity 1. So this is T infinity 1. And then this surface will have some temperature, let us say TS1. TS. And this one will say, let us say this is TC1. C stands for contact surface. And this side, let us say TC2. And this side, let's say TS2. And this is T infinity 2. So this will be T infinity 2. Now these are the temperatures involved, and let us combine them with the resistances. So there are 5 resistances here. I will draw a new diagram so that it will be much clearer. So T infinity 1, TS1, TC1, TC2, TS2, T infinity 2. TS, TS plus 1, T1, TC2, TS2, T infinity. Okay, now the resistance between T infinity 1 and TS1. So this region is a convective resistance. I will say convective resistance, and these are conductive. And this again is a convective. We know that convective resistance is 1 by HA, and conductive resistance is L by KA. Okay, so this convective resistance will be 1 by HA. So A is, we have seen A is 5 meters square. So 1 by HA will be 1 by H is 10. 10 into 5. And this conduction resistance inside uh, slab A will be L by Ka. So thickness of the slab is 8 millimeters and K is 0.09. So 8 into 10 power minus 3 divided by 0.09 multiplied by 5. Then second conduction resistance, the thickness is 16 millimeters and conductivity is 0.03. So 16 multiplied by 10 power minus 3 divided by 0.03 multiplied by 5. Sorry. In between these two, so this will be the conduction resistance here. Here, this is the contact in between. This is the contact, and we already know that the contact resistance is 0.06. So this is 0.06. Already know. And this convection is 1 by HA. H is 20. So 1 by 20 multiplied by 5. Okay. And we know T infinity 1 is 200 degrees. T infinity 2 is 40. 200 degrees Celsius, and this is 40 degrees Celsius. Now the total resistance, overall resistance will be 1 by 10 multiplied by 5 plus 8 multiplied by 10 power minus 3 divided by 0.09 multiplied by 5 plus 0.06 plus 16 multiplied by 10 power minus 3 divided by 0.03 multiplied by 5 plus 1 by 20 multiplied by 5. So this we need to calculate. So 0.02 plus 0.0178 plus 0.06 plus 0.1067 plus 1 by 1 by 100, 0.01. So this is 0.2145 Kelvin per watt. So this is the total resistance. So once we know the total resistance, we can calculate the value of Q. The heat transfer is delta T overall divided by the total resistance. Delta T overall is T infinity 1 minus T infinity 2 divided by R. So 200 minus 40 divided by 0.45 equal to 745.9 watts. So this is the heat that is being transferred across each of these sections. So from the fluid to the wall, inside the first slab, inside the contact resistance, inside slab B, and the fluid outside wall B. All of these are carrying a heat in series, a heat of 745.9 watt. Okay, so we need to find out. So we have answered the first part of the problem. We found out what is the rate of heat transfer. So rate of heat transfer is 745.9 watts. We should also plot the temperature profile. So for that, what we need to do is to estimate the temperature. So what temperatures do we need? Wall temperature of A, and in between A and B, there's a contact resistance. So the temperatures here we need to find out, and also the temperature of the wall on the outside of B. So only then we'll be able to plot the temperature. So we need to find out 4 temperatures. So let us start with the left side. We know the heat transfer from the fluid to the wall surface. We know the heat transfer coefficient. We know that heat is transferred using convection method. So from here to here, we can evaluate the heat transfer using convection and the temperature difference T infinity 1 minus TS1. So using that, we can find out the value of TS1. So we'll proceed like this. So we'll start from the left hand side, first estimate T1, and using you estimate TS1, then using a TS1, we can estimate the value of TC1, then TC2, and finally TB also. So that we'll use the heat transfer that we have just assumed. So on the left side, the heat transferred Q is equal to HA delta T. So H is given in the problem as 10 multiplied by area is 5 multiplied by delta T is again what's the temperature 200 minus TS1. This will be equal to 745. So using this equation, I can calculate what is TS1. This will be divided by 185.1 degrees Celsius. Okay. Now in slab B, in slab A, Q is equal to Ka delta T. Okay. So K on the slab is 0.09 multiplied by area is 5 multiplied by delta T is delta T by delta X. Okay. Delta T is TS1 minus TC1 divided by delta X. Thickness is 8 millimeters. So 8 multiplied by 10 power minus 3. This is equal to 745.9. We know TS1. We should find TC1. So from this TC1 we can find out. So $171.9. TC1 is 171.9. And next, inside the contact, that means this region, the heat transferred Q is equal to delta T by R. Delta T is TC1 minus TC2 divided by the resistance. I have found the resistance to be 0.06. So that value we can use is equal to 745.9. Now we know TC1 is 171.9. So we can find out TC2. T2 is equal to so that should be 127.1. Then finally, one more temperature is left. So this surface temperature on the wall B. So that is we represent it as TS2. We find out TS2 on wall B. Q is equal to, again we use convection equation because there is and here. We can also use the heat transfer equation between in the slab. So take this temperature and use it in the delta T and this thickness is 16. That is one way. Other way is to use this convection condition for same answer. So Q is HA delta T. So H is by 5 multiplied by TS2 minus T infinity 2 is equal to 745.9. Now I know T infinity 2, so I can find out TS2. What is T infinity 2? It is 40. So TS2. is 47.5. Yes, Celsius. Okay. So now we know all the temperatures. We need to do is sketch the temperature distribution. I'll create a new slide so that now we will draw the slabs. So T infinity one is 40, no? This side was actually 200 degrees Celsius. So 200 degrees Celsius, and this side is 40 degrees Celsius, and this temperature got it as 185 point. So this is, I'll just write it down. TS1 is 185.1. TC1 is TC2 is 27. TS2 I look at the values here. TS1 is 185, so very high value compared to the other end. TS2 is 47.5. So let us start plotting somewhere here. Let us say this is TS1. This is 185.1 degrees Celsius. Then TC1, that is temperature on this surface, is 171.9. So slight drop is there. So this is the temperature, 171.9. Then TC2 is 127. So compared to 171.9, there is almost 43, 44 degrees Celsius drop. So that is quite a considerable drop. So let us say this is this one. So this is 127.1 degrees Celsius. And finally here 47.5. So this is 127. So 47.5, that is quite a drop. 47.5. So you can have to connect them with a straight line because the profile inside a slab is a straight line. So this is the temperature distribution. On the left hand side, there is a convective environment. So 200 degrees Celsius. So this is, will be something like this. And on the right hand side, 40 degrees Celsius convective environment. So this will be something like this. So this is the temperature distribution. So to plot the temperature distribution, you should also know what is the temperature at each and every location. So for that, you have to use the heat transfer and find out the temperatures. So is it clear? See the problem. It took almost what's the time now? It's about 11:20. So it took almost 35 minutes to solve, but it's actually a simple problem. I because I was writing everything in detail and explaining, but in reality, if you have sufficient amount of practice, it doesn't take this long. Okay. So it will pause for 1 or 2 minutes and ask some, take some questions. If you have any questions, you can ask now. Any questions? Anybody has a question? See, what we have done is the resistance is there now that we have converted to a slab and we have represented as a thermal resistance of a slab, added it as a slab in series with the given two slabs. So in reality, this slab is a fictitious slab, doesn't really exist. So in reality, how we should plot the temperature profile is like this. So initially we have only two slabs. So we should plot only two slabs. So there is this 185 degrees Celsius and 171 and then 127 is 171.9, 127.1. So this is the drop that is taking place across the contact. And finally, 47.5 is in the surface, and then the convective environment will take some temperature, something like this. So this is 200 degrees Celsius, and this is 40 degrees Celsius. So this is the correct way of drawing the temperature profile, because you see we have given it some thickness here, but it's not really representative of the contact resistance. It's only fictitious that we have introduced for the sake of convenience to use the concepts of the composite slab. Okay, so when you plot the temperature profile, use this method and not this method. All right, so we'll move on to the next problem. I think we have taken considerable amount of time for this problem, so the next problem will need more time. So I think we'll not be able to complete it. Anyway, we'll start. So here there is an uninsulated thin-walled pipe of 100 millimeter diameter is used to transport water to equipment that operates outdoors and uses the water as a coolant. Okay, so there is a pipe carrying water. During particularly harsh winter conditions, the pipe wall achieves a temperature of minus 15 degrees Celsius, and a cylindrical layer of ice forms on the inner surface of the wall. If the mean water temperature is 3 degrees Celsius and a convection coefficient of 2000 watt per meter Kelvin is maintained at the inner surface of ice, which is at 0 degrees Celsius, what is the thickness of the ice layer? So this is the problem. So let us draw a schematic diagram of this. Always I insist on drawing a schematic diagram. So here also I'm trying to draw a simple schematic. It doesn't have to be a beautiful diagram, but it should be informative. So this is a pipe is carrying water. So this is water flow direction. We are interested in this circular cross section only. So here we are told that the surface temperature during this is minus 15 degrees Celsius. And okay, the diameter. Then we have the mean water temperature is 363 degrees 1000 watt per minute. Inside this pipe, and this pipe hasn't got any thickness. We are told that it's a thick is a 3 degrees Celsius. H is a 2000. So 2000 watts per meter square Kelvin is a high value of heat transfer coefficient. So this is water is flowing at 3 degrees Celsius, and what is happening is a cylindrical layer of ice forms on the inner surface of the wall. The inner surface of the wall, and it is freezing. So you see in this core, liquid water is flowing, but liquid water at 3 degrees Celsius. But what is happening here? On the surface, the temperature is minus 15. So here, the water temperature is above zero, and the surface temperature of this pipe is below zero. So there is a transition taking place from positive temperature to negative temperature. That means somewhere the temperature crosses zero, touches zero before it becomes negative. So that zero temperature for water is the freezing temperature, and therefore a thin layer of ice is forming in this region. So this has frozen. Convection coefficient of is maintained. So this it's given as 0 degrees Celsius. So this is the information given. What is the thickness of the ice layer? What is this thickness? So this is, if we look at the cross section, circular cross section, we have two circles. One is, let us say, this is R1 and this is R2. So now we have a situation where we have a hollow cylinder or cylindrical shell with the convection inside, and we have to find out what is the thickness. That means what is of ice is R2 minus R1. That's all. This is the entire thing. There we actually are given the diameter. Therefore, R2 is 100 by 2 is 50 millimeters. The only thing is we have to find out the value of R1. So this is what we need to do. Okay. So basically what is the thing that is happening here is heat is convected from this water to this ice and from this ice to the surface. So there is some steady state conditions prevailing. Using the steady state conditions, we should be able to calculate what is the value of R1 so that we can evaluate R2 minus R1. So now this particular problem, you see that there is in the temperature profile of a cylinder, there is a logarithm involved. So solving for the logarithm, you need to utilize some equation solving approaches that also I will discuss. But as of today, the time is up. So we'll stop today and we'll continue tomorrow. So continue tomorrow. All right, give me your attendance. Rutunidhi,
Present, sir.
Ilash,
Present, sir.
and Cherian,
Present, sir.
Sudan, Leap, Arth,
So Siddharth present, sir.
Vatsan,
Present, sir.
Present, sir.
Danivel, Tamilalagan,
Present, sir.
Niranjan, Vaibhav Karan.
Present, sir.
Present, sir.
Is it Vaibhav?
Abhijit. No,
Abhijit
Abhijit
Karan?
present, sir.
Sir,
Present, sir.
Vaibhav present.
Sir, Kriti Krishna present, sir. Kriti Krishna.
Praveen, Adil Singh,
Present, sir.
Sadil present, sir.
Chaturvedi, Chaturvedi.
Present, sir.
Who is that?
Chaturvedi present, sir.
Chintan,
Present, sir. Chintan present, sir.
Ayush Tripathi,
Sir, Hamza Hassan present, sir.
Ayush
Thank you.
Tripathi,
Present, sir.
Harshvardhan,
Present, sir.
Hemant Kumar,
Present, sir.
Pa,
Present, sir.
Chandramouli Pratap Singh,
Present, sir. Shubh.
Sai Rohit,
Present, sir.
Aman,
Sriraman present, sir.
Vishal,
Present, sir.
Deepesh,
Present, sir.
Venkat,
Yes, sir.
Sundar Krishna,
Sundar present, sir.
Pranav,
Pranav present, sir.
Yanti,
Present, sir.
Sriniket present, sir.
Adri Narayanan, Vito,
Present, sir.
Ajit,
Ajit present, sir.
Harish Raghav,
Yes, sir.
Rahul,
Present, sir.
Rose,
Present, sir.
R,
Present, sir.
Present, sir.
Gauri Shankar,
Present, sir.
Tishwar,
Motisho present, sir.
Prakash,
Present, sir.
Pooja,
Present, sir.
Kumar,
Yes, sir.
Karan Sarvesh,
Present, sir.
Ajay,
Present, sir.
Arnold Simon,
Present, sir.
Vamsi Krishna, Venkatesh,
Present, sir.
Shaya,
Present, sir.
Randev,
Yes, sir.
Varun,
Present, sir.
Kunal Rao, Vignesh Krishna,
Yes, sir.
Shant Madhur,
Present, sir.
Present, sir.
Present, sir.
Priya Vasan,
Present, sir.
Kalai Priyan,
Chat box, sir.
Narayanan,
Present, sir.
Anish present, sir.
Raj,
Yes, sir.
Keshav Kumar,
Present, sir.
Present, sir.
Karthik Prasanna,
Present, sir.
Kadri Kuppam Sai Kaustubh,
Present, sir.
Runahalyan,
Present, sir.
Sarvesh Krishnan, LC Femina,
Present, sir.
Present, sir.
Jeffet Gionel,
Present, sir.
Manu,
Present, sir.
will call once again. Madhusudan,
Present, sir.
Deep, Trishant, Palanivel,
Prashant present, sir.
Sir, Pioneer present, sir.
Trishant,
Prashant present, sir.
Niranjan,
Present, sir.
Chandramouli Pratap Singh, Sri Kumaran,
Present, sir.
Badri Narayanan, Vamsi Krishna,
Present, sir.
Kunal Rao,
Not present, sir.
Kunal Rao, Kalai Priyan,
Kalipin put in chat box, sir.
Sarvesh Krishnan. All right. So we'll meet tomorrow and we'll try to complete the available problems. Okay. And also, I think we have a couple of minutes, so I'll just give you the link for software so that you can download.
Sir, is this for the practicing, sir? That for
This one,
this software, sir. Okay, sir.
it's just to introduce you to a tool that is available. Okay. It's not a part of the curriculum. You can say it's a part of the digital initiative. So I posted that link here. So this software actually comes along with an ebook of Incropera and David. So it also has got some worked out examples and so on. So you can go through that, and if time permits, if you are interested, you can practice. Anyway, I will introduce you briefly to the software in one of these classes. Okay. All right. So you can leave.
Thank you, sir.
Thank you, sir.
Yeah. Thank you.
Sir, Sarvesh Krishnan present, sir.
Sarvesh Krishna, do you post?
Yes, sir.
What's the number?
19 BME 1327.
See, Sri Kumaran, Niranjan, you have posted your names. I can read your name, but I don't know your number. I'll have to search for your number, okay? Save me the trouble. Whenever you post in the message box, give the number also.
Sir, I can give you the number, sir. Hello, sir.
Just a moment, wait.
Sir, others can leave, no, sir?
Yes, yes.
Thank you, sir.
Yeah. Sri Kumaran. What's his number?
Sir, Niranjan 19 BME 1061, sir.
Okay, fine.